Hello friends, myself Dr. Nandakumar Raubole from College of Engineering Ambazugai is going to deal with Applied Thermodynamics 1. This is our 43th lecture. So in previous lecture we have discussed about introduction to air compressor, then applications of compressed air, classification of air compressor, components of air compressor, terminology, work done per kg of air compressed without clearance. It was proposed to cover work done per kg of air compressed with clearance and volumetric efficiency, but we could not cover in previous lecture. So today we will be looking at the terms, the work done per kg of air compressed with clearance. So this was proposed or expected to be covered in previous lecture, but unfortunately because of lack of time we could not cover. Volumetric efficiency was proposed in previous lecture itself. So today we will cover isothermal efficiency also. Methods of improving isothermal efficiency of a air compressor and multi-stage compression, and what are the advantages of multi-stage compression. So these are the things that we will be covering in today's lecture. So now, very first, we will see the work done per kg of air compressed with clearance volume. What is this clearance volume? So as we know, this piston moves from top dead center to the bottom dead center. So if this piston reaches to the topmost position, it hits to the cylinder head. Piston head hits to the cylinder head. Therefore, to avoid this, there will be a clearance. Though this piston is not allowed to reach up to the topmost position, it will reach up to certain position, and there will be a clearance between piston head and cylinder head. When piston reaches to the top dead center, intentionally some clearance is left, and this clearance is to avoid damage to the cylinder head and piston head, as well as to the walls mounted over the cylinder head. Now this clearance, whether this clearance is having any kind of effect on the work done required to run the compressor or not, that has to be seen. So this clearance is intentionally provided in the compressor. So actually clearance is there. So how this works, that we see. Initially the air is present, say for example piston is at bottom dead center, BDC is at bottom dead center. So the moment of piston in top upward direction starts to compress air. So air is compressed from point 1 to 2. So initially pressure is P1 and volume is V1, and air is compressed from P1 V1 to volume pressure P2 and volume V2 P2 V2. So the law of compression is known as a polytropic compression process. So it is compressed according to PV raised to n is equal to constant. So as soon as the pressure reaches to the maximum pressure P2, then the delivery valve opens and the air starts to reach, air is started to allow into the air is passed into the reservoir. So air starts to deliver from point 2 to 3. So when this piston is somewhere here at point 2, say this is at point 1, when it reaches to point 2, delivery valve opens. At that time only pressure is reached to the P2. So further movement of piston from point 2 to 3, say point 2 to 3, delivers the air to the reservoir. So as this piston reaches to the top dead center, now top dead center is here, TDC. So there is a clearance, means here some part of air is going to remain, and then this piston starts to move in the downward direction. So initially it starts from 1, compresses it up to point 2, and it discharges air from point 2 to 3. So this piston is not allowed to move beyond this point 3. So the moment of piston towards bottom dead center is going to expand the air present in this clearance. So this air which is present in this clearance starts to expand because this piston moves from top dead center towards bottom dead center. So here the air which is present in this clearance is going to expand polytropically from point 3 to 4. So when this pressure reaches again to atmospheric pressure, then the inlet wall opens and the fresh air enters into the compressor. At point 4, the suction starts. Actually, suction does not start at point 3. So first, the air which is present in this clearance volume is going to expand from pressure P2 to P1, and then from point 4 onwards the suction process takes place. So this is the actual amount of air sucked, but this is the stroke length of piston. So piston moves from this point to this point, so this is stroke length, so that's why we call as a swept volume Vs. So here the actually air is sucked from point 4 to 1, so this is known as the actual amount of air sucked into the compressor. So swept volume is greater than actual volume of air taken into the compressor. Again, this piston starts to move from bottom dead center towards top dead center. Compression process starts. As soon as piston reaches or pressure reaches to P2, the delivery valve opens. The delivery process takes place from 2 to 3, and after point 3 the piston starts to move towards bottom dead center, leaving this clearance space. So from point 1 it reaches to 2, pressure reaches to highest pressure, then delivery valve opens. Further movement of piston allows this air to move into the reservoir, and when it reaches to point 3, then this piston starts to move in the downward direction. The air present, which is compressed air present in this clearance volume, starts to expand polytropically unless piston reaches to the point 4. So when it reaches to the point 4, the expansion process stops because the pressure of air reaches to the atmospheric pressure, and then inlet valve opens, and as soon as inlet valve opens, so this air will be atmospheric air enters into the compressor cylinder and it sucks. So this suction process is from 4 to 1. So this is the actual volume of air taken into the compressor cylinder. So it is expected theoretically, this is the swept volume Vs. So it has to start to suck the air from point 3 to 1. So practically it does not happen. Now this volume which is not covered by piston, which is at the topmost position of this piston when piston reaches to TDC, so this volume is known as the clearance volume, which is represented here on PV diagram. We see this is the clearance volume, then from point 3 to 1 this is swept volume, and 4 to 1 it is a actual volume of air sucked, and P1 is the inlet pressure whereas P2 is the delivery pressure. So both the processes are going to follow polytropic. So compression is polytropic and expansion is polytropic. Say we assume that polytropic index PV raised to N1 is equal to constant, and expansion process PV raised to N2 is equal to constant. We may assume like this also. So we may have polytropic index different for compression and different for expansion also. So this is how the process takes place. Now the work done required to compress air with clearance is given by this orange color area highlighted in this diagram. So this much of work is required. So this work is not required for compression. So initially we calculate the complete area and then we subtract this area which is expansion. So for expansion no work is required because the air which is in this cylinder is already compressed, and the moment of piston need not to put any effort to expand this air because the pressure of air is higher, and it will push this air to piston to move in the downward direction. So work is done by the compressed air. So when we are going to compress air, so this is the work consumed by compressor, whereas this is not the work consumed by compressor, this is work done by the air on the piston. So here this is positive work and this is negative work. Negative work in the sense work consumed by the compressor. Work done on a system is negative, work done by the system is positive. So here work is done by the system, here work is done on the system. So now we'll see how this is calculated. Now the work done per cycle is equal to area 1 2 3 4 1. So area 1 2 3 4 1. This area gives us work done. So now this work done, W is equal to work of compression minus work of expansion. So work done during compression, here we consider as a positive. So work done of compression WC minus of work done during expansion. So these two have opposite sign. So now WC, work done during compression, WC is given by area area 1 2 5 6 1. So 1 2 5 6 1. So this area gives us work done during compression, and work done during expansion WE is given by area 3 4 6 5 3 3 4 6 5 3. This is the work done during expansion. Now we know work done during compression without clearance is already calculated, which is given by N divided by N minus 1 P1 P1 P2 divided by P1 to the power of N minus 1 divided by N minus of 1. So this is the work done which we have calculated in previous lecture. So this is in Newton meter per cycle. So this is equation number 1 we can call, which we have calculated in previous lecture. Now work done during expansion can be obtained. Work done during expansion can be given by N divided by N minus 1 P4 P4 P3 divided by P4 to the power of N minus 1 divided by N minus 1 Newton meter per cycle. So we call this as equation number 2. So work done during compression is given by P1 V1, this initial pressure, initial volume, highest pressure divided by lowest pressure, P2 divided by P1 to the power of N minus 1 divided by N. So now expansion work WE is N divided by N minus 1 P4 V4. So this is the lower point P4. In place of 1 we are writing P4 V4. Then P3 highest pressure divided by lowest pressure P4. P3 is equal to P2. P3 is equal to P2. So here P3 divided by P4 to the power of N minus 1 divided by N minus 1. So instead of P1 we have written as 4 P4 V1. Instead of V1 we have written as V4. Instead of P2 we have written it as P3, and instead of P1 we have written as P4. So this is applied to process 1 to 2. And this is applied to the process 3 to 4. The only thing is this work is considered as positive, this is considered as negative. So now we can write this as P3 is equal to P2. We can see here pressure at point 3 is equal to P2. Pressure at point 3, 2 and 5 is same, that is P2. P3 is equal to P2, and pressure P4, pressure at point 4, point 1 and 6 is same. So that is nothing but P4 is equal to P1. So now again we can write this work of expansion as, work of expansion can be written as n divided by n minus 1. So equation number 2 can be rewritten as P1 sorry P1 V4 P1 V4 in bracket, in place of P3 we can write P2 divided by P1 to the power of n minus 1 divided by n minus 1. So this is Newton meter per cycle. We can call this as equation number 3. So already we have written here, say, equation number A. So in this equation number A, net work done in this case, when we consider clearance, is nothing but work done during compression minus work done during expansion. So subtracting equation number 3 from equation number 1, we get the work done. So subtracting equation 3 from equation 1, we get work done W is equal to WC minus of WE. This can be written as n divided by n minus 1 P1 V1 P2 divided by P1 to the power of n minus 1 minus 1 minus of expansion work is n divided by n minus 1 P1 V4 in bracket P2 divided by P1 the power of n minus 1 divided by n minus 1. On simplification, n divided by n minus 1 is common, n divided by n minus 1, P1 is common, P1 is taken common, so this bracket is also common. Bracket we can write here 2 divided by P1 to the power of n minus 1 divided by n minus 1. So V1 minus V4 can be written. So this is not common. So here V1 minus V4. So V1 minus V4 is written there. So now what we can see here, n divided by n minus 1 as it is, V1 as it is. Now we will find here V1 minus V4 is nothing but VA, actual volume of air taken. So V1 minus VA equal to V1 minus V4 from PV diagram. Therefore we can write in place of V1 minus V4 as VA in bracket P2 divided by P1 to the power of n minus 1 divided by n minus 1. Now this P1 VA can be written as RT1 or P1 VA is equal to, can be written as MAR T1. So therefore this equation can be written as n divided by n minus 1 or T1 bracket P2 divided by P1 to the power of n minus 1 divided by n minus 1. We can call this as equation number 4. This gives work done in Newton meter per cycle for per kg of work done. So this is work done per kg, because m is equal to 1 we are going to assume. M is equal to 1. If we assume m is equal to 1, we call this as a PV is equal to RT. So in place of P1 VA, we are going to write it as RT1. So now if we compare work done with the original equation which we have obtained with the without considering clearance, so both the equations are same. Therefore, we can conclude here that the clearance volume does not affect the work of compression. This is the work of compression per kg of air. So equation number 4 is same as the work done required for compression of air without clearance. Just we can see here. So this equation which is here, work for compression without clearance is P1 V1. In place of P1 V1 we can write as RT1. So equation number 1 is same as equation number 4. So there is no much difference in the work done required if we consider even clearance also. Now coming to the volumetric efficiency. What this volumetric efficiency is? Volumetric efficiency of compressor is the ratio of actual free air delivered to the displacement of the compressor. So actual free air delivered is VA and displacement of compressor is VS. So this ratio is known as a volumetric efficiency. So the actual volume delivered by compressor is V1 minus V4. So V1 minus V4. So suction starts from 4 to 1. So this is the actual air taken into the compressor suction. So this much of fresh air is taken and this much of fresh air is delivered. Whereas this clearance air is expanded, and we can find this swept volume. Actually piston moves for a distance of 3 to 1. So this is the swept volume. So Vs. So the ratio of Va divided by Vs gives us the volumetric efficiency. So now this volumetric efficiency is given by Va divided by Vs, or we can call this as Va is nothing but V1 minus V4. Va is nothing but V1 minus V4. Va is equal to V1 minus V4 and Vs is equal to V1 minus V3. V1 minus of V3 gives us Vs, so swept volume. Now writing this again as V1 is equal to Vc plus of Vs minus of V4 divided by Vs. So in denominator V1 minus V3 is Vs. So this V1 is nothing but sum of clearance volume plus swept volume. So V1 is nothing but sum of swept volume plus clearance volume. So this plus this gives us V1. So V1 equal to Vc plus of Vs. So substituting V1 is equal to, in place of this V1, Vc plus of Vs. V4 as it is. In place of V1 minus V3 we are substituting as Vs. So again we can rearrange this equation as Vs minus of V4 minus of Vc. So here Vs is taken here, minus sign is taken common, therefore V4 becomes plus and this Vc becomes minus. So if we multiply this again by minus, so same numerator we can get divided by Vs. So only rearranging this term, Vs is taken first, minus is taken common. So as minus is taken common, this V4 in bracket becomes plus and this Vc which is plus when it enters into this bracket becomes minus. So if we simplify this bracket, again numerator will be same. So now again rearranging this, so Vs minus of Vc is taken common in this numerator, Vc, V4 divided by Vc minus of 1 written here in numerator and divided by Vs in the denominator. So now again simplification, if we divide complete numerator by Vs, so Vs divided by Vs gets cancelled, 1 minus of Vc divided by Vs bracket V4 divided by Vc minus 1. So now this can be written as 1 minus K divided by 100 into V4 divided by Vc minus 1. So where the clearance volume of compressor is always even in terms of percentage stroke volume and denoted by K, term K. So here this K is nothing but K is equal to Vc divided by Vs into 100. Therefore K divided by 100 is Vc divided by Vs is taken. So here we can write this as K divided by 100 is equal to Vc divided by Vs. So Vc divided by Vs is replaced by K divided by 100. This is volumetric efficiency. Now again we'll write here as P3 V3 to the power of n is equal to P4 V4 to the power of n. So P3 V3 is nothing but clearance volume. V3 is nothing but clearance volume. So we can write this as a Vc to the power of n is equal to P4, means pressure at 4 is 1. So P4, so P3 is taken as P2. P3 is taken as P2. So pressure at point 3 is equal to P2. So P2 Vc is equal to P1 V4 to the power of n. So how we have written this as P2 is equal to P3 and V3 is equal to Vc and P4 is equal to P1. So polytropic law, P3 V3 to the power of n is equal to P4 V4 to the power of n. Applying polytropic law for compression and expansion, we get this. Now we can rewrite this as V4 divided by Vc. V4 divided by Vc is equal to P2 divided by P1 to the power of 1 over n. Now this volumetric efficiency, which was given as 1 minus of K divided by 100 into V4 divided by Vc minus 1. So this equation becomes now 1 minus K divided by 100 bracket. In place of V4 by Vc, we can write as P2 divided by P1 to the power of 1 over n minus 1. So this can be replaced from equation given above. This is replaced in place of V4 divided by Vc. So in place of that, we can write P2 divided by P1 minus 1. So this is how we obtain the equation for volumetric efficiency. Equation for volumetric efficiency given by this, or it is Va divided by Vc. So now coming to the next thing, that is isothermal efficiency of a reciprocating compressor. So here on PV diagram, when we represent the polytropic process and isothermal process, so this process 1 to 2 dash is a isothermal process. What is this isothermal process? It is a process during which temperature remains constant, T is equal to constant, and follows the law PV is equal to constant. So here the air is compressed in such a way that the temperature is not allowed to increase. That means sufficient time is given for compression process, and the minor rise in the temperature is not noticed, because the compression process is so slow that the amount of heat generated is immediately dissipated, and the process of compression takes place at constant temperature. So that is known as isothermal compression process. So during isothermal compression, so work done required is very less, because the area below this isothermal curve is less, and if we follow polytropic law, then the additional work is required. So this the area which is shown here is the additional work required for compression of air. So here we can say, in case of isothermal process, the work done required is less than the polytropic process. So therefore we can call the work required to run compressor becomes minimum if compression follows the isothermal law. Instead of following polytropic law, if we compress the air isothermally, then work required is less. But this isothermal process practically is not possible, because we are going to do compression process very fast. Just we have seen that in 1 second 5 cycles are completed. That is 1/5 of second is provided to complete 1 cycle. So it is bound to increase the temperature of compressor, and the process of compression does not take place at constant temperature or isothermal. So the efforts have to be made to attain the isothermal process during compression. So now what we can say, the work required to run compressor becomes minimum if the compression follows isothermal process. The work, this is not possible practically, it is not possible to follow isothermal process. Now the work done per kg of air delivered when compression is polytropic, the work done per kg of air when compression is polytropic is given as actual work. We can call this as actual work because actually we can compress here polytropically. Isothermally is not possible, so we call it as actual work. W actual is equal to N divided by N minus 1 RT1 in bracket P2 divided by P1 to the power of N minus 1 divided by N minus 1. This is Newton meter per cycle. Now, the work done per kg of compression if the process is isothermal. Work done per kg when compression is isothermal. Isothermal is given by area 1, 2 dash, 3, 4 and 1 on PV diagram. So this area 1, 2 dash, 3, 4 and 1, this is the area which is which gives the work done during isothermal process. So if it follows the polytropic process, the area 1, 2, 3, 4, 1 gives the work done required in the polytropic compression. So now, so isothermal work isothermal work is equal to P1 V1 so P2 V2 initially in previous way P2 V2 plus of polytropic isothermal work is P1 V1 log to the base E V1 divided by V2 dash. So P2 V2 is this area to V2 dash, we can call this as P2 V2 dash. So P2 V2 dash, so this area plus of area below this isothermal curve V1 V1 log E log to the base E V1 divided by V2 dash minus of P1 V1. So P1 V1, this area is subtracted. Type of derivation we did. The first term and last term is same, whereas this intermediate term in previous case it was P2 V2 minus P1 V1 divided by N minus 1 because the process was polytropic compression. So now on simplification we can rewrite this equation as P1 V1 log to the base E V1 divided by V2 dash plus of P2 V2 dash minus of P1 V1. So now what we can say here is P2 V2 dash P2 V2 as if we apply polytropic isothermal process P1 V1 is equal to constant or P1 V1 is equal to P2 V2, but here in place of V2 it is V2 dash. So P1 V1 is equal to P2 V2 dash. So both are same. So we cancel this and the work done during isothermal process can be written as P1 V1 log to the base E V1 divided by V2 dash. So this isothermal work can again be written as, so first we write this as P1 V1 log to the base E V1 divided by V2 dash, or else this can be written as P1 V1 in place of P1 V1 this can be written as RT1 log to the base E V1 divided by V2 dash, or this can be written as RT1 log to the base E in place of V1 divided by V2 dash V1 divided by V2 dash is written as P2 divided by P1. So this can be written as P2 divided by P1. So from this, substituting V1 divided by V2 dash, V1 divided by V2 dash, we can write this as P2 divided by P1. Again, this is Newton meter per cycle. So these are the so many equations. So isothermal work can be given by first combination or second combination or third combination, any one. So now what we can write here is from PV diagram, the saving in work we can see here, this is the saving in work. If we follow polytropic process, this much of work is required, this complete work is required. If we follow isothermal, then only the area below this curve is required. So saving in the work per kg, saving in the work per kg of air if the compression is isothermal instead of polytropic. The area one, two, 2-1 is work saving. It is given by delta W, work saved. Delta W is equal to W actual minus of isothermal work. So now this gives us work saving. Now we can write this equation. Actual work done is N divided by N minus 1 RT1 in bracket. We can write this as P2 divided by P1 to the power of N minus 1 divided by N. So this actual work done minus 1 minus of isothermal work is R P1 log to the base E P2 divided by P1. So we can take RT1 as common. So this is RT1 in bracket N divided by N minus 1 P2 divided by P1 the power of N minus 1 divided by N minus 1 minus of log to the base E P2 divided by P1. So this much is the work saving delta W. So this area is shown represented by hatching lines is given by this. So Newton meter per cycle the work saving. Therefore the isothermal efficiency of compressor is defined as is the ratio of isothermal work to the actual work, that is isothermal efficiency equal to isothermal work divided by actual work. So this is written as isothermal work is RT1 log to the base E P2 divided by P1 whole divided by N divided by N minus 1 RT1 in bracket P2 divided by P1 to the power of N minus 1 divided by N minus 1. Close this bracket. RT1 gets cancelled. So this is log base E P2 divided by P1 whole divided by N divided by N minus 1 bracket P2 divided by P1 to the power of N minus 1 divided by N minus 1. So this is isothermal efficiency of a compressor. So now, what are the methods for increasing isothermal efficiency? So whenever it is possible to compress air isothermally, because the isothermal process follows the constant temperature T is equal to C, and it needs to be it needs sufficient time is to be given for compression process if we want to achieve isothermal compression. Therefore, it is not possible to attain the isothermal compression process perfectly. Therefore, certain methods are adopted to enhance the efficiency to reach isothermal efficiency to some extent. So here the methods which are used is spray injection method. So spray injection method, in this spray injection method, cold water is injected into the compressor cylinder in order to cool the air. So temperature is lowered. The aim is to reduce the temperature of air during compression process. So the water is injected into the compressor cylinder to reduce its temperature. The second method is to provide water jacket around the compressor cylinder. So in order to carry away the heat produced during compression, water jacketing is provided, and that water carries out heat, thereby reducing the work done required. And third one is intercooling. So what is this intercooling? Air is not compressed from directly from pressure P1 to P2. It is compressed to some intermediate pressure. So it is compressed from P1 to Pi, and then it is cooled in a intercooler, and again it is compressed from Pi to P2. So this is the process of intercooling, reduces the temperature of air in between and reduces the work done. So another method is the external fins are provided. So if this is the cylinder, so on this surface of cylinder, fins are provided to dissipate heat to the atmosphere, so that the temperature in the compressor cylinder is reduced, and reduced temperature in the compressor cylinder reduces the work done required for compression process. These are the four methods to improve the efficiency, isothermal efficiency of a compressor. That is nothing but isothermal work we cannot achieve, but actual work is reduced. So if we reduce actual work required for compression, then isothermal efficiency is going to improve. So isothermal work is always going to be constant, so denominator is reduced. So by reducing denominator, isothermal efficiency is improved. So how to reduce denominator is these are the methods. So actual work required for compression of air is reduced by spray injection or water jacketing or intercooling or external fins. So this is the only method. We cannot improve isothermal isothermal work required. We can reduce the actual work required for compression by these four different methods. Now we will see what is multi-stage compression. So air is allowed to pass into low pressure cylinder LP cylinder having larger diameter and stroke length L. So when it is passed into this LP cylinder, air is compressed to pressure P2, and then it is passed into the intercooler where temperature of air is reduced, so it is cooled, Again, the air which is coming out from the intercooler at pressure P2 is passed into the high pressure cylinder. So stroke length is going to be same as the stroke length of LP cylinder, but the diameter of LP cylinder is larger, whereas diameter of HP cylinder is less, because the volume of air is reduced. Same volume has to be occupied in this HP cylinder. Again, air is compressed and then it is delivered to the receiver. So now we can see here how this is achieved. So now this 1 to 4 dash represents isothermal curve, just now we have seen, which follows the law PV raised to PV is equal to constant, and this process 1 to 6 is nothing but polytropic process PV raised to N is equal to constant. So it is not possible for us to compress here by following this isothermal process. So now what happens here? Air is compressed from 1 to 2 in LP cylinder, low pressure cylinder. When it reaches 2.2, then the air is passed into the intercooler and temperature of air is reduced. So when temperature is reduced, again it is passed into the second cylinder, which we call as HP cylinder, and then the compressed air is taken out. So from pressure P1 it is compressed to pressure P2. At pressure P2 it is cooled, and then again it is compressed. So this much of work is saved in multi-staging. So this is how we call as the multi-stage compression. So temperature of air is reduced from T2 to T3. If we succeed in reducing temperature of air from T3 to T3 dash, so temperature of isothermal process is attained. So it is called as a perfect cooling. In case of perfect cooling, temperature from T2 to T3, instead of reducing it from T2 to T3, temperature is reduced from T2 to T3 dash. So when temperature at point 2 is reduced to T3 dash, then we call it as a perfect intercooling. So when, for example, air enters at 27 degrees Celsius into the compressor, and when it comes out, it comes at 50 degrees Celsius, and it is again cooled. So when it is cooled, and the temperature of intercooled air when comes out of intercooler, again if it is 27 degrees Celsius, that is same as that of inlet temperature, then we call it as a perfect cooling. So temperature at point 3, if it is equal to the temperature of air entering at T1, then we call it as a perfect intercooling. Imperfect intercooling gives us T1 is not equal to T3. T1 is not equal to T3. T3 is greater than T1. But if we cool this air, first we compress it from 1 to 2, then it is cooled perfectly, and again it is compressed, so work saving will be larger. Perfect cooling saves work larger. So if we are going to cool it up to here, so this much of work is saved, so complete work is saved. So here it is tried to cool this air in this intercooler to have the perfect intercooling. So now advantages of multi-stage compression. What are the advantages of multi-stage compression with intercooler? So first of all, the work done per kg can be reduced. So work done required is reduced. And second one, better mechanical balance can be achieved. So how better mechanical balance can be achieved? So we can see here there are two cylinders. So there will be a reciprocating mass which is to be balanced. So these two cylinders are arranged on a same crankshaft in such a way that the imbalanced masses will be balanced by each other. These two cylinders will balance the imbalanced masses, and the perfect balancing is achieved. That is one of the advantage of having multi-stage compression. Then third one is pressure and temperature range in each stage is reduced. So if it is compressed in one stage, then the pressure ranges from P1 to P2 directly, P1 to final pressure. So if it is compressed in multiple stages, the pressure range and temperature range is reduced, and loss of air due to leakage is less, because the LP cylinder is allowed with certain clearance, then HP cylinder has got tight clearance, less clearance, there will be less leakage. That care can be taken. If we compress air in single stage, very high pressure air, into the LP cylinder itself or single cylinder will have tendency to leak out. The third one is volumetric efficiency is higher. So if we have a multiple stage compression, then we can have the increase in volumetric efficiency. That is nothing but there will be low resistance for the movement of air into the compressor, as the clearance actual volume which is taken can be improved by running the LP cylinder at lower speed by providing more time for air to enter into the compressor. And then HP cylinder is designed to withstand high pressure. LP cylinder need not to be designed to withstand high pressure, only HP cylinder is to be concentrated. So design considerations and costing of HP cylinder will increase, whereas LP cylinder will be less. So these are the advantages of having multi-stage compression.